Picture a towering mountain, perfectly still against the skyline. Everything seems so peaceful, right? The air is calm, the ground is quiet. But that stillness, it's a complete illusion. Because deep underground, a massive, highly pressurized engine of molten rock and expanding gas is waking up. And the journey from that deep slumber to a violent surface explosion is hands down one of the most dramatic and terrifying processes on our planet. Before a volcano erupts, something is already happening deep beneath the ground. Today, in this explainer, we're going to trace that hidden, subterranean mystery step by step to figure out exactly how the Earth warns us when a disaster is brewing. Let's kick things off with Section 1, the magma awakens. So miles beneath us, extreme heat makes magma buoyant, giving it this initial upward push. But heat alone, it's just not enough to trigger a massive eruption. Magma is actually packed with dissolved gases. As it rises and the surrounding pressure starts to drop, those dissolved gases begin to form bubbles. This absolutely crucial process is called vesiculation. You can think of it just like shaking up a warm bottle of soda. Those trapped bubbles desperately want to expand, and they really want to escape. And that creates a very distinct chain reaction inside the volcano's plumbing system. First, the magma ascends. Then, those trapped gas bubbles expand. Finally, that immense internal pressure violently forces the magma upward. It's the true engine of an eruption. Actually, if a column of magma doesn't have enough gas bubbles in it, it simply won't erupt. It literally lacks the explosive driving force needed to break through to the surface. Which brings us to Section 2, quakes and fractured rock. As all that pressurized magma forces its way up, it physically has to stretch and break the solid rock above it just to make room. This rupturing leaves behind high-frequency seismic clues, what scientists call volcanotectonic or VT seismicity. But here's an incredibly fascinating detail. These earthquake swarms usually don't start right under the summit. They often strike at distal locations along tectonic faults, sometimes tens of kilometers laterally away from where the eruption will eventually happen. It acts like this built-in subterranean early warning system. Now, knowing that magma is down there violently shattering solid rock, you might be wondering, can these early warning earthquakes destroy buildings and roads? Like, if a volcano is about to explode, the quakes leading up to it must be completely devastating, right? Well, the crucial thing to know is that these precursor earthquakes rarely ever exceed a magnitude 5. So sure, they're strong enough to sway some trees or maybe cause a bit of light damage, but they aren't going to collapse the city or destroy major roads. The rock is breaking, yeah, but it's happening in smaller, continuous swarms rather than one giant catastrophic rupture. All right, moving on to Section 3, swelling and toxic breath. As the pressurized magma gets closer to the surface, the volcano actually physically changes shape. Filling that subterranean reservoir pushes the Earth's surface upward and outward. Think of it exactly like inflating a balloon that's buried under a few layers of sand. The ground literally has to swell up to accommodate the rising pressure. Alongside that subtle swelling of the ground, the volcanoes start showing rapid surface symptoms. It basically takes on this toxic breath. The heat and escaping gases begin altering the chemistry and temperature of the local water. You'll see noticeable steaming, enlarged patches of hot ground, and dangerous changes in fumarolic gases, things like sulfur dioxide and carbon dioxide, bleeding right out into the air. So, how do we track all this? That's Section 4, the science of monitoring. To read these subterranean clues, scientists become sort of geological detectives. And the tools they use for ground deformation monitoring have mind-blowing precision. We're talking about detecting changes down to just 1 part per million. To put that into perspective, that's like being able to detect a single drop of vermouth mixed into 16 gallons of gin. It's almost unbelievable. Take tilt meters, for example. These measure the minute swelling of the volcano's slope. To understand just how sensitive they are, imagine slipping a single tiny dime under one end of a wooden board that is a full kilometer long. That is exactly how carefully scientists are listening to the mountain's breathing. Scientists have an incredible arsenal of technology at their disposal. Seismometers track the continuous tremors of gas, magma, and breaking rock. Tilt meters and lasers measure that microscopic ground swelling we just talked about. And up in space, satellites provide a critical eye in the sky, detecting subtle thermal anomalies, elevated gas emissions, and tracking ash plumes if things do kick off. Altogether, this tech lets us forecast and track the rising magma we've been following today. But here comes the twist. In Section 5, not a certain eruption. Just as the tension peaks, the mountain is swollen, rock is fracturing, toxic gas is venting, we have to realize something absolutely crucial. A pressurized, swelling magma reservoir does not always guarantee an impending eruption. Look at this comparison. On one hand, you have Mount Pinatubo in 1991, where massive precursor earthquakes perfectly warned us of a giant historic eruption. But on the other hand, look at Campi Flegrei in Italy. That volcano has shown massive swelling and seismic unrest for over 60 years, and still no eruption. The terrifying reality is that all of these precursors can continue for weeks, months, or even years, or they can just subside at any time without an eruption. Why does that happen? Well, sometimes a cooling lava cap blocks the surface. It loses its gas, becomes colder and denser, and basically stalls the magma column below. The magma loses its gas pressure, the delicate balance is broken, and the whole thing shrinks back underground, safely out of sight. The mountain just goes back to sleep. The mechanics of our planet are as complex as they are powerful. An eruption is never just a surface event. It's the grand finale of a long, unseen struggle involving intense heat, expanding gas, immense pressure, and shattered rock. The eruption begins above the ground, but the warning signs often begin deep beneath our feet. Keep that in mind the next time you're looking at a quiet, majestic mountain. You have to wonder, what other invisible, pressurized forces are quietly building right beneath us? Thanks for joining me on this explainer, and stay curious.